we work with TSMC today. That is our primary fab partner, and a lot of the prototyping work we do is with TSMC. And they have a lot of programs where you can try out your ideas on a smaller scale, where you can build smaller chips and test out your technology ideas. And we have done a lot of that. We actually, for every generation of product, we've typically done a few test chips before we productized it. And they've been very supportive, and it is very possible to do that. So that's kind of been our way of getting our products to market and testing out our technology before we actually productize it.
This episode of Eye on AI is sponsored by the DFINITY Foundation. DFINITY Foundation is a Swiss not-for-profit that is home to some of the world's leading cryptographers, computer scientists, and experts in distributed computing. Their mission is to shift cloud computing toward a fully decentralized state by supporting the Internet Computer, also known as ICP. If you don't understand anything about the Internet Computer, you can see my episode with Dominic Williams. ICP's vision is that most of the world's software will be replaced by network resident software that's an evolution of traditional smart contracts. To achieve this vision, ICP is designed to make smart contracts as powerful as traditional software, all while remaining tamper-proof, unstoppable, transparent, and verifiable. Since DFINITY's launch in 2016, they stand as Switzerland's most extensive blockchain research and development initiative and have been awarded more than 500 research grants worldwide. DFINITY remains steadfast in its mission to drive the advancement of the decentralized internet. Network resident software can now be used to run AI models and RAG infrastructure, preventing them from becoming quote-unquote hot wallets from where data can be stolen and increasing resilience. Furthermore, the technology has been designed to allow AI models to spin up and modify running web applications and internet services solo by addressing several key challenges. If you're interested in reading more about the Internet Computer, visit internetcomputer.org. I also encourage you to listen to my episode with Dominic Williams, in which he explains the Internet Computer.
So thanks for having me on the podcast. I've been systems and semiconductor guy for many, many, many years. Started my career at Intel in the mid 90s. Actually, I spent the first 10 years of my career being a chip designer, and I, spent a lot of time doing different portions of the design work at Intel in the first 5 years that I was there. Um, Worked on circuits, bleeding edge circuits for the Pentium processors. Worked on system issues related to bringing up processors. After that, I went to a startup called Eleros, which was focused on building interconnect chips for Ethernet applications. So that was the next 5 years of my career. So really, the first 10 years of my career were spent in heavy R&D and really working on both processor chips and chips built for interconnects and networking. After that, I want to say, I transitioned. I was still at the startup, and I was looking to transition into something that was more customer facing, and moved into a business role. Spent another 5 years working on different aspects of what it takes to take a product to market. Right, really focused on go to market, and and I had an advantage because I was essentially taking the chips that I had helped build and working with customers to figure out how to deploy them and making them useful, so to speak, for those customers. Um, After which I transitioned to a bigger role at a company called Infi, and Infi was in the high-speed networking and high-speed interconnect space. They were looking to break into the data center market. They had a really good, footprint in the telco market, but were looking to break into the data center market. So I went there and incubated a business for them, which was only focused on data centers, and that was a huge success for the team. We spent about 9 years building that business that eventually grew to 2.5 billion in revenue from zero, and was acquired by Marvell in 2021 in a $10 billion acquisition. I stepped out in 2019 to start D-Matrix because I was getting very excited by the inference computing opportunity.
Mhm.
And I know it sounds very obvious today, but it wasn't very obvious back then, right? A lot of the narrative was about training and training bigger models and doing inference with image classification, and image models were really the all the rage back then.
Mhm.
um, and we quickly realized that it didn't make much sense for us to go do something with training because that was a market that was well capitalized, a lot of investment. Didn't make much sense for us to go after the inference market in the edge that was focused on images and image classification. So we kind of were looking for a new entry point, and that is how we started focusing a lot on language and transformers. And I'll talk more about that as we talk about the D-Matrix journey. But that's been my journey. I grew up in India in a family of entrepreneurs. Both my grandfathers were entrepreneurs back in the 1940s, left home to start their businesses. My father was an entrepreneur too, left his home, came to the US, worked here, went back and started a business. Entrepreneurship is probably in my DNA somewhere. It was a matter of time before I, stepped out and did something of my own. And here I am, taking my shot at this. We'll see where it goes.
Yeah. Well, let's talk about D-Matrix's products and how you establish market share in a market that is so heavily dominated by NVIDIA and the other big players.
Yeah. So I think I've lived through the process of building a semiconductor business before. As I was, stating earlier in my introduction, I was when I was at Infi, we essentially incubated a business to enter the data center market. Building interconnects for data centers, and what we saw was, and I'll come to your question in a bit, but
Mm.
this perspective is important because that answers the question that you just asked, which is in the semiconductor business, especially when you're building chips, they're very capital intensive, obviously, and take a long time, multiple generations of product to get to success. And the only way to really be successful is to really intercept some kind of a discontinuity in the market. There has to be some kind of transition that is underway, and you need to intercept that transition at the right time. So at Infi, the transition that we intercepted, there's really two major transitions that happened at the same time. Was that data centers were going optical. Most data centers used to be based on copper interconnect, but they were transitioning to optical interconnect because obviously the speeds were getting to a point, bandwidth was becoming very, very critical, and the higher the bandwidths, the harder it gets to run signals over copper. So it was transitioning to optical. And the other thing that was also happening at the same time was the signaling standard, which used to be NRZ, which is the 1-0 standard, was transitioning over to PAM based signaling. So 4-level signaling. So we were going from a 2-level signaling standard to a 4-level signaling standard. And so that required new electronics, new optics. And so you had this tech transition and a market transition happening at the same time. And that is what we intercepted very successfully. And the incumbent back then were companies like Broadcom and Marvell, and they were giants, right? But Infi was successfully able to break into the market and dislodge some of the incumbents and build a very successful business doing that, right? So same thing applies for where we are today. We see major transition happening in the market again. Obviously, There is the whole transition from general purpose computing to accelerated computing, which is a mega change that is happening across data centers. But within that accelerated computing, we are also seeing the market transitioning away from training to inference, and
Mhm.
inference becoming a very relevant workload. And that is also a tech transition because you need a fundamentally different architecture as you migrate away from training, which is predominantly a performance oriented workload, to inference, which is an efficiency oriented workload. So you can't really build a common platform that does both training and inference. You can, it's not like you can't, people have done it, but it's not going to be, it's like building a Swiss Army knife, right? You're trying to do too much with the same thing. Building a dedicated inferencing solution, given that inference is going to be a much larger portion of the opportunity for AI compute, which means we think a dedicated solution for inference is going to win, right? And that's what we are focused on at D-Matrix, and that's why we think we can find enough share in the market to build a very valuable company.
Yeah, I have to ask. I live not far from IBM Research, and uh, I was over there the other day talking to their head of chip design, and he was saying they have a fab up, I think, in Poughkeepsie where they do uh, pilots or proof of concepts or whatever.
Hmm.
Uh, so once you've designed a chip, which is a feat in itself, where do you go to build a prototype and see if it's working?
So we do all our work. We first of all we are building a product that is is built on standard CMOS process technology. So we are not doing anything funky here with the process technology that requires us to go to boutique fabs and build partnerships with fabs that work on very exotic processes and process technology and whatnot, right? So standard CMOS logic process. So we can work with TSMC, we can work with Samsung, right? We work with TSMC today. That is our primary fab partner, and a lot of the prototyping work we do is with TSMC. And they have a lot of programs where you can try out your ideas on a smaller scale, and what they call the MPW program, or a shuttle program, where you can build smaller chips and test out your technology ideas. And we have done a lot of that. We actually, for every generation of product, we've typically done a few test chips before we productized it. Um, and they've been very supportive, and it is very possible to do that. So that's kind of been our way of getting our products to market and testing out our technology before we actually productize it.
Yeah, and as far as the inference market goes, as
Hmm.
I was saying before we started recording, I've spoken to Cerebras and Sambanova. Uh, with training, NVIDIA has a lock because developers are used to using CUDA,
Yep.
and they don't want to have to learn a whole nother um, programming language, I guess, or uh, instruction set and all of that. Uh, but with inference, developers are primarily using uh, hardware in the cloud and through API, so they don't have to worry about building on top of the
Hmm.
chip. Is that the opportunity as well that you see, and how does D Matrix? I mean, I had a conversation yesterday with Google Cloud uh, asking about how these new accelerators get a footprint in the cloud. And I know Samanova and Cerebras are all both building their own clouds until there's enough of an uptake that the hyperscalers will offer clusters of their chips. So how do you do that?
Yeah. So, we've first of all, the team at D Matrix has successfully sold into the hyperscalers before, right? We've been through call it 10, 15 hyperscaler ramps with products, not at D Matrix, but through our prior experience, right? So
Mhm.
we know what it takes to ramp a product at a hyperscaler. We've been doing it for 20 years, right? When Google first had a cloud offering, um, and not necessarily a cloud offering, but they were setting up infrastructure to power their own applications. They was setting up pretty enormous data center infrastructure back in 2007, 2008. We were building chips that would help them power that infrastructure, right? This was back many many moons ago. So my startup from the 2000s, when we were building chips to connect networking uh, equipment. We were selling products into Google to help them power their infrastructure. So, and all the way from back then to the Infi journey, where we had our chips sitting in pretty much every hyperscaler on the planet, all four big hyperscalers here in the US, three in China. So we have a lot of experience when it comes to deploying product at hyperscalers. We know the anatomy of what a typical hyperscaler ramp looks like. We know what the hyperscalers are typically looking for and how they engage, right? So at Dmatrix, we are kind of modeling our business along similar lines. We're building product that would embed into the equipment and infrastructure that the hyperscalers are deploying. So we are not going to them saying, "Look, you need to rip and replace what you have to accommodate us." Right? We are looking at their equipment and we try to understand what they deploy, and we try to fit inside what they already have without them having to rip out stuff to accommodate us. So really what we are trying to do is a cloud augmentation play, right? So we can go and we build accelerator cards, and maybe I can show you the card while we are
Yeah.
on that topic. So yeah, this is our 600-watt Corsair accelerator card. It's a PCIe card, and it's got two chips here that you can see. Each chip has four chiplets, so there's a collection of eight chiplets sitting on a single card that are connected to each other in an any to any configuration. And then if you turn this card around, there's a lot of DDR memory that is sitting at the back. This is a pretty dense card. It's like a 24 layer card. A lot of engineering that has gone into making this, because we have a lot of interesting chiplet technology that goes onto this card that needs to be routed very efficiently. So that's the guts of the card, and then that gets packaged into this accelerator unit. You see two cards there put together, and then they are connected with a bridge on top, which allows every chip on every card to talk to a chip on the other card directly, right? So from a software perspective, this is treated like a single unit from a software perspective. So just
Mm.
as NVIDIA has NVLink, we have the ability to connect all these chips sitting across these two accelerators into a single config from a software perspective, right? So that allows us to unlock a lot of efficiencies when we are running inference. Um, so coming back to your question, I mean that's what we ship. That's a card we ship. That's a unit we ship, and that plugs into any AI server that is built by folks like Dell or HP or Supermicro or Lenovo, or call it even if it's a custom server sitting at one of the hyperscalers, as long as it can house a PCIe card, we can plug into that socket and augment that server for AI inference. So that is our go-to-market model, where we go to the hyperscalers and we tell them, "Hey, you've got a fleet of servers that currently don't have our hardware in them. But what if you were to put our hardware into the fleet of servers? we could augment that entire fleet with a solution that will completely change the economics of doing generative AI inference. Now, wouldn't that be attractive to you? And they pretty much across the board love that, right? Because it doesn't require them to pull out and rip out stuff, but it allows us to integrate our solution into theirs, and then they can go augment that fleet with more capability.
And talk a little bit about the technologies involved in this chip.
Hmm.
You're putting the weights directly uh, on SRAM. Is that right? Which, as I recall, is what at least what Cerebrus is doing. I think Sambanova stacks memory on top of the chips. I don't remember, but the static random access memory has the model weights
Yeah,
directly
yeah,
uh, uh, in them.
yeah.
Can you talk about that? How that uh, speeds things up? How it's more energy efficient, and then talk about the chiplet architecture.
Yeah, sure. So a few questions in that one question. So let me unpack some of that for the audience, right? So first of all, um, the chiplets themselves, right? So you see this is a chip here. There's obviously a lid that if we kind of pull that lid off, you'd see four chiplets inside a chip here and four here. So there's a total of eight chiplets sitting on this 600-watt PCI card. If I remember correctly, the only other 600-watt PCI card on the market is the Hopper H200. Blackwells are still not available in a PCIe form factor. Still, I'm sure they will make those, but there's currently not available. So the only PCIe accelerator from NVIDIA that's the latest and greatest is the H200. Now, the H200 has about 800 millimeter square of silicon on a 600-watt card, right?
Mhm.
We have across these two chips 3200 millimeter square of silicon. So that's four times the amount of silicon that is sitting on this card at the same power envelope, in the same power envelope, 600 watts, compared to the latest and greatest NVIDIA offering. And the reason we are able to do that is because of the chiplet technology and the chiplet approach, and obviously a lot of design techniques that we have built into the chiplets that allow us to run the chiplets in a highly energy efficient manner. So we have almost 4x the amount of silicon on the same 600-watt power envelope, right? And so what's in that? What's in those chiplets, right? So obviously we've got a lot of compute, um, but again, the bottleneck is not compute, right? If you look at generative AI inference, the bottleneck is really memory bandwidth and then eventually memory capacity, and it's about finding the right balance between compute, memory bandwidth, and memory capacity. And that's what we have strived for on this solution, right? So we have um, obviously 10 petaflops of compute on that card that I just showed you, on 10 petaflops of 4-bit compute sitting on that one card, which is plenty for now. And but the key thing is to optimize around memory bandwidth. Now, you talked about putting the weights in SRAM. We have a combination of our in-memory compute and SRAM on those chiplets. So there's a combination of call it across that one card we have almost 2000 in-memory computing cores, and we have a lot of SRAM also that is built into those chiplets. So we have almost 2 gigabytes of what we call high performance memory. So this is memory that is sitting on the chiplets directly, but running at a very, very high bandwidth, call it 150 terabytes per second of bandwidth. You compare that to HBM memory that is sitting at, roughly about, 4.8 terabytes or, 5 terabytes. The Blackwells are closer to 8 or 10, but the Hopper that I, was comparing our product to, because that's the only other PCIe product, is sitting at about 5 terabytes, right? So there's almost like a 20x 20 to 20 30x improvement on memory bandwidth. Now that is where we kind of punch through the memory wall, right? it's not about just having a lot of compute, but it is having a lot of compute and a lot of memory bandwidth to go along with it, so you can feed that compute very efficiently from memory, and the memory is local. Now, uh, there's about 2 gigabytes of that, which is typically not enough for a lot of the AI models. So we scale this up further. So we'll have 8 PCI cards sitting in a single server, and then we have 8 servers sitting in a single rack. So we have a collection of 64 cards sitting in a single rack. So 64 times 2 gigabytes is about 128 gigabytes of that high performance memory that is sitting in a single rack. With that 128 gigabytes, we can easily comfortably serve 70 billion parameter models or 100 billion parameter models out of a single rack, which is for the most part plenty for anyone who, most enterprises, most, very high end enthusiasts, many sovereign opportunities that we are going after, including some of the hyperscaler opportunities. 100 billion parameter model sizes are pretty attractive. They can cover a lot of ground with that type of model. Now, there are frontier models that are much larger, and we can certainly run the frontier models across multiple racks, or even out of the capacity memory that I showed you. There is, DDR memory sitting at the back. We can
Yeah.
run trillions of multiple trillion parameter models running out of that capacity memory. They would run a lot slower, but you can run them out of that capacity memory. So we have the ability to do this. We have this flexible memory architecture where we can run 100 billion parameter models in a single rack, or we can do more across multiple racks. But it's running at these extremely high speeds because of the memory bandwidth problem that we addressed. And all this is possible while embedding our hardware in a customer's environment without having them having to purchase the whole solution from us, right? We can go augment their infrastructure with our solutions and give them the benefits of running what we call, ultra low latency batched inference, right? So extremely fast while allowing the user to batch multiple, or the customer to batch multiple users. So really, that's what we bring to the table. It's a unique combination of this chiplet in memory compute, technology, highly energy efficient design, how we connect the chiplets to each other, the numerics. We have 4-bit numerics and 8-bit numerics that are block floating point, which is now becoming a standard for inference. All of this goodness built into this one solution, one PCI card form factor that can go augment our customers' fleets with, and supercharge those fleets for generative AI inference, low latency generative AI inference.
And are most of your implementations on premise, or are they? Is it this primarily a cloud solution? It seems with inference that market growing, and as large enterprises um, start using generative AI, that a lot of they're putting it in on premise because they don't want their data to leave.
Yeah,
Um, is
yeah,
Yeah.
yeah. I mean, it's both. I think we are really quite agnostic, right? As I was stating earlier, we our go-to market is built on taking our solutions and augmenting our customer solutions, right? So we don't quite care whether the solutions are in the cloud or in the enterprise, but the journey for most AI deployments is starting in the cloud, right? So I think our journey is starting in the cloud today, whether it's sovereign clouds or what we call GPU clouds or neo clouds, which is the smaller dedicated AI clouds, and then there is the hyperscaler clouds. So these are really the three focus areas for us today, and then over time this will migrate into on-prem enterprise clouds, and we'll migrate as the workloads migrate there. But right now, the high velocity deployments are happening in the clouds, that are public clouds, and then eventually they will go to the private clouds over time.
Yeah. The Where do you see this going? I mean, as I said, I mean, NVIDIA has such a dominant position. Is uh, the market opening up. I mean, as I was saying too, if you're in the cloud and this is for inference, uh, what matters is speed and cost. Uh, do developers care what chip is giving them inference? I mean, do they make that decision, or is that if it's in the cloud, is that a decision that's being made by the cloud provider?
Yes, yes. So typically, I think you need a person who really understands the application that they're trying to accelerate. And what is happening is there's plenty of data that suggests that applications which are highly interactive with the user tend to be more successful, meaning the users are more likely to stay with an application that really interacts with them, right? Anything that is more offline in the interaction, doesn't tend to keep users around for too long, right? So anything that draws eyeballs is stuff that is highly interactive. So latency matters, right? Clearly. So you need to look at the application. I mean, there is obviously other constraints like cost and energy efficiency and whatnot, size of the model, how big is the model, and you got to kind of look at the whole picture to figure out what kind of underlying accelerator hardware could really allow for a better user experience and a better cost profile, right? um, so it's a combination of these things. So yes, the hyperscalers have the people, have the right expertise and the right you know folks with the right set of skills to make those calls. They can match the right hardware to the right application, right? And then they can go deploy and they also have the ability to go deploy new accelerators in their fleet to enable that user experience. So if a new accelerator solution can demonstrate that we can improve the user experience, which is latency, or we can improve cost, or we can improve things like energy efficiency by a factor of at least 2 to 4x, that is a big win typically for a customer, right? So if you have the latest and greatest NVIDIA hardware and you can show a 2 to 4x improvement over that in that generation, that's a big win. That's a very big win, right? So again, for inference, I like to say it has been hard to beat NVIDIA on training, and they've done a terrific job of keep anybody who was at GTC earlier this week and saw the keynote. I mean, they've done a terrific job of advancing their roadmap, and they have a roadmap that goes out 4 years and 5 years, and it's almost impossible to kind of play catch up there with all the technology that they bring. Well, when it comes to inference, I think there is no one size fits all. You can't really take a big rack of Blackwells and just throw it at every inferencing problem. It's not going to work. It's not like every single inference request looks the same. uh, Inference requests can be latency, may need to be latency optimized, may need to be cost optimized, may need to be throughput optimized, right? So there is no one size fits all. You can't say like here is one piece of hardware that's going to serve all of inference, right? It's difficult to do that. So inferencing fleets are going to be heterogeneous. There's going to be GPUs, there's going to be CPUs, there's going to be accelerators, and that is what we are focused on. We are not saying that we are going to be the best at everything, but we are really good at low latency batched inferencing. So anytime you need multiple users where each user needs a really interactive experience, that's where you need to think of D-Matrix.
Yeah. I spoke a couple of years ago, and I was just looking to see if they're still independent. But there was a company, Rescale, that has kind of an orchestration uh, technology that plugs into all the clouds, and then you give them your your inference problem, and they automatically route you to whichever cloud has the correct chip or the correct
Yep.
resources. Is that something that you work with people like that?
Yes, yes. We work. So by the way, we worked with Rescale. We know them well, and they're. But you're absolutely right. I think that kind of skill set, by the way, already exists at the hyperscalers.
Mhm.
So they're not they either partner or they have the skills inside the company to build that orchestration layer. In their case, they are doing query profiling. They have a query coming from a user. They're trying to batch that query based on the profile of that query, right? Whether it's a query that is latency optimized query, or is a throughput optimized query, or a cost optimized query. So depending on the region it comes from, right, you may have to route the query to the right data center, and so on and so forth, right? So I think there is just a lot of things you need to kind of take into consideration before you decide where you want to send that query. And um, so yes, that orchestration layer, I mean, NVIDIA announced Dynamo at GTC this year. That is again an orchestration layer for inference queries, right? So yes, that is going to be very important, because again, going back to the fact that inference is not a one size fits all. Not every query is the same, so you need this orchestration layer that is going to be able to efficiently route queries to the right hardware, right? And we are seeing a lot more of that, and that is going to be where inferencing hardware is more heterogeneous. It is not just all GPUs, right? And that is something that gradually I think will become clear to a lot of people, but it's pretty clear to us.
Does it matter which model uh, you're using, and when you put the weights on the chip or on the PCI card, or however you say it, um, uh, that's a decision that you're making, or that's a decision that the customer is making?
It's typically done in conjunction with the customer, right? So the customer is trying to solve for a certain problem, and they work with us to figure out what's the best way to get there, right? So there's again different vectors, right? There's things like the model size, there is the model quantization, there is the software stack, which is okay. You know, my model is highly customized, and I need to write my own custom kernels to for that particular model. How do I bring those kernels to your hardware, right? Oh, I want to focus a lot on latency. Oh, I want to focus a lot on cost, right? I mean, so there are all these different things that go into consideration. Cannot be done in isolation. It is a highly uh, it's typically a very deep engagement with a customer to kind of get these models deployed. Now sometimes you have models like Llama 3, call it 70 billion or 8 billion, and you want to deploy those models. It's a lot easier, and that's why you're seeing companies getting into that business, which is I'm just hosting Llama models, right?
Yeah.
Mistral, DeepSeek, these are all open source models and available and readily available, and they all look a lot like each other. I mean, they're all variants of Llama to a certain extent, variants of transformer models to a certain extent. So once you've done work on a few of them, you can actually incrementally take that work to others, right? So it becomes a lot easier to host those. So you're seeing more of that becoming very popular, right? We'll be doing that too. Of course, we are not going to get into the hosting business. That's not something we do, but we'll be enabling a lot of folks to host models of that family, that variant, with our hardware.
Yeah.
Um, yeah.
As more of these models come out, how easy is it to load a model onto the chip? I mean, if you've got you know chips with Llama 3 on them, and then suddenly DeepSeek comes out with something that blows Llama 3 away, which I
Yeah.
guess it already has.
Yeah.
Uh, how do you then switch? Can you? How do you do that? Yeah.
Yeah. So it depends again, what that new model looks like DeepSeek R1 Distill, which is a distill version of DeepSeek, the
Hmm.
reasoning model, right? It is essentially, it looks a lot like Llama, right? It is so if you've done work on Llama 370 billion, uh, the incremental work needed to do, bring DeepSeek R1 Distill onto your hardware is not like it's going to take you, 6 months, right? It's going to take you probably a few weeks actually to
Hmm.
bring that solution, because the kernels look very similar. The model architecture, yes, there are changes, but it's for the most part you can leverage a lot of the work you've done, right? So it is a few weeks worth of work, and you can onboard a new model, right? um, so that's really what it comes down to, is what does the model architecture look like, things like how many layers in the model, are there any new mathematical operators that the model introduced so that you have to write new kernels, right? What is how big is the model? What is the scale out strategy, right? What is the scale up strategy? How do you partition that model? Any kind of parallelism techniques that you need to apply. A lot of this work across the models we just talked about, can carry forward, right? So
Mhm.
that means your incremental work is a lot less. Um, so yes, it really depends on from model to model. I don't think there's a generic rule that you can apply across every single model.
Mhm. And where do you see this going as models proliferate? Uh, are are chips going to proliferate as well? And is the inference market growing so fast that there's plenty of room for everybody, or is there going to be a shakeout at some point where, I mean, the hardware business is expensive, and
Yeah.
yeah.
I think the market is big, right? So the opportunity is massive. I don't think there's been a creation of an opportunity like this one in our lifetimes, right? So the inference computing opportunity. I mean, if you believe what Jensen said at the GTC, I mean, it's almost 10 times larger. There's 100x more compute needed. The opportunity itself is 10 times larger, right? So if the training opportunity was 100 billion, then the inferencing opportunity could be 1 trillion, right? I mean, let's scale that down a little bit. I mean, even if it is a 2 to 300 billion dollar opportunity, right? That's massive. That's massive. I mean, you're looking at the creation of the entire semiconductor market is 500 billion. So you're looking at the creation of another 300 billion dollar opportunity just in the next 10 years, which is going to support a lot of different company. And we talked about inference not being a one size fits all. So it's not like there's going to be just one solution that runs away with the prize, right? So yes, there will be multiple players. The question is, it's not going to be as many as we have today, right? So there'll be some kind of consolidation that'll happen over the next, call it 5 years, maybe. But there's going to be multiple winners because, first of all, the market, just the inherent nature of inference is such that you can't really build a single chip that covers all your needs. And that is going to allow other companies to break out. And that would be kind of the healthy outcome anyway. I think, in the semiconductor industry, we've not had the creation of a yet another large semiconductor company in the last 20 plus years, right? Because the industry went through a lot of consolidation, and this the return on semiconductor investments was not very attractive, so not many companies got funded. So we have had a very long gap where we have not had any company really break out. So I think this platform shift, this AI platform shift, is going to drive that, and this is going to lead to the creation of the next NVIDIA, the next Broadcom, the next Marvell, call it. Um, and I would expect that to happen, right? And it would be good for the ecosystem.
Yeah. Are you, TSMC is building this fab in Arizona. I think they're going to start with 4 nanometer and eventually get to two. Are you going to be manufacturing in Arizona when they're up and running?
Yeah, probably. I mean, again, the way TSMC is also going to have this, similar fabs in Taiwan. So they're going to have a 4 nanometer in Taiwan, um, and the pricing structure could be different just given the cost of labor between Taiwan and the US. So we'll take a look at it, and we'll right now we run everything out of Taiwan, which is we are at 6 nanometers at TSMC, and that's kind of exclusively run out of Taiwan. Our product roadmap goes to 4 and then eventually to 2, and we'll have the option of running out of Arizona. We don't have to take that up. We can always still keep running out of Taiwan, but we'll have to just see, what makes most sense from a business perspective at that point in time, and then make a decision.
Yeah. And your market is, I would guess, for the time being, primarily in the United States. But I ran into Andrew Feldman and Rodrigo Liang in Riyadh, Saudi Arabia, last fall, and they were both there. Obviously, we were at a conference, but they were uh, talking to Aramco and some of the big inference companies or companies looking for inference. How much of your market is outside the United States, and where would it be concentrated?
Yeah. So yes, we are working with customers outside the U.S. We have customers in the Middle East. We have customers in the APAC region. Um, we have customers in Japan, right? So we are working with customers outside of the U.S. We do believe that our primary market will be in the U.S. Because that is really where most of the high volume deployments are happening. And we talked about our go-to-market model. It's a little different from the companies you mentioned, right? We are focused more on embedding our hardware into a customer's environment, right? We and so it's a volume-driven business for us, and for that, by that token, we are looking for very large fleets of server AI server hardware that can be augmented with our solution. And that typically today, at least, given that China is off limits with all the trade, the trade tension and trade wars, for now we can't ship our product into China. Um, so that means the US market is going to be a huge focus. The markets I talked about, APAC and the Middle East, still don't have the ability to house our product. They're looking for total solutions. So our dependence on those markets is going to be limited for some time. Yeah.
Why, or maybe I'm just unaware of it, but I mean, not including China, why are there not uh, chip companies sprouting up in India, for example, or are there that are competing with you guys?
They've begun to spring up. I mean, there's a couple of reasons. One is, I think, just the perception is that the software ecosystem in India is a lot stronger than the hardware ecosystem, and that is true, right? There's just a lot more software talent in India than there is hardware talent, and but there is good hardware talent, right? And but the startup ecosystem around hardware in India is not that robust yet, right? So there is not enough capital to feed these companies. The markets are not in India. The markets are predominantly in the US and China or Japan or elsewhere, right? Um, so it's hard for a company to establish itself and say, I'm going to build product for international markets. Uh, and be successful, right? Because there is always a company that is already doing that in the US for the US markets, or there is a company in China doing it for the China market, right? So then building a company in India to serve those markets when the startup ecosystem for hardware is already not that robust is making it makes it very, very challenging.
Yeah. China has done a lot since the chip. I mean, Huawei has done a lot,
Hmm.
and it was kind of the leading edge of the chip embargo. Uh, and China has a lot of talent. It has a lot of hardware talent, and they're working very hard at developing their own uh, ultra. What is it? The UH. I'll cut this out, but the lithography machines needed to etch, uh, you know, 7 nanometer chips.
Yeah.
Um, are they going to be a player in this market eventually, or are they already?
You're talking about the EUV machines,
Ultra high,
extreme ultraviolet, extreme ultraviolet. Yeah, yeah, yeah. So, and your question is, are they going to be a player building those machines?
in providing inference chips to the global market.
Oh, inference chips to the global market. Okay, got it. Um, to be seen. To be seen. I think. I mean, there's just a lot of embargoes right now on China with getting access to the latest and greatest technology. So it's hard for them to really keep pace with the US on a certain class of technology and inferencing chips. Um, So yeah, it's difficult to say whether they will they will be able to keep pace with innovation in the US. I think, to me, the US is currently on the forefront of just the latest and greatest techniques when it comes to chip design, right? Chip manufacturing, chip not necessarily manufacturing, but chip design specifically, and architecture, and we just have a very robust ecosystem of engineers and customers and partners who put it all together, right? Um, I know, by the way, but even before these embargoes came and the trade tension escalated, right? I think the U.S. always had a lead when it came to building cutting edge chips. So it is independent, by the way, of what's happened in the last, call it, 8 years or 10 years, right? Um, so and it's only the gap is only widening now because of the trade tension. So I would argue that the U.S. will be the one to produce bleeding edge, cutting edge inferencing chips, at least for the next 5 to 10 years, right, for the global market, and it'll be difficult for other markets to really keep up.
Yeah. Yeah. Okay. Well, we're almost up to an hour. Is there anything I haven't asked that you think listeners should know?
Yeah, I mean, D-Matrix is a great place to come work. So if anyone in your audience is looking to work on really bleeding edge, inferencing chips, where we kind of are solving some really hard, technical problems of both software and hardware, right? Compilers, infrastructure software, runtime systems, software, scale out, scale up, chiplet technology, chiplet interconnects, compute technology, packaging, board design. I mean, come talk to us. We'd love to talk to you, and we are growing the team, and we are the only company that has a purpose built generative AI inferencing solution built from the grounds up for inference. It's not like we started the company doing something else and then pivoted into this opportunity. We built this company for generative AI inference, right? Just given the timing of when we started, it worked out that way. So we are super excited about the opportunity that we are growing into, and this is your chance to come work on something super exciting.
This episode of Eye on AI is sponsored by the DFINITY Foundation. DFINITY Foundation is a Swiss not for profit that is home to some of the world's leading cryptographers, computer scientists, and experts in distributed computing. Their mission is to shift cloud computing toward a fully decentralized state by supporting the Internet Computer, also known as ICP. If you don't understand anything about the Internet Computer, you can see my episode with Dominic Williams. ICP's vision is that most of the world's software will be replaced by network resident software that's an evolution of traditional smart contracts. To achieve this vision, ICP is designed to make smart contracts as powerful as traditional software, all while remaining tamper proof, unstoppable, transparent, and verifiable. Since DFINITY's launch in 2016, they stand as Switzerland's most extensive blockchain research and development initiative and have been awarded more than 500 research grants worldwide. DFINITY remains steadfast in its mission to drive the advancement of the decentralized internet. Network resident software can now be used to run AI models and RAG infrastructure, preventing them from becoming quote unquote hot wallets from where data can be stolen and increasing resilience. Furthermore, the technology has been designed to allow AI models to spin up and modify running web applications and internet services solo by addressing several key challenges. If you're interested in reading more about the Internet Computer, visit internetcomputer.org. I also encourage you to listen to my episode with Dominic Williams, in which he explains the Internet Computer.